Good day. Now, for today's session, we are going to be having another concept in our journey on chemistry. This would be our next round in our concept of chemistry that we started in the last session. Now, in our earlier session, we looked at the concept of what comprises the element. We are talking about the atom itself, and in that atom, we are talking about the proton, neutron, and electron. We talked about the fact that, of course, the Dalton atomic theory defines that the atom is the smallest indivisible part of an element, and that for that atom, we can find within the nucleus of that atom the proton and the neutron, and then orbiting around the circumference in this case, or orbiting around the atom or the nucleus of the atom, we will find the electron, right? We talked about this briefly as the concept of what the atom comprises of. So this was the first part of the disproofs into the Dalton atomic theorem that says the atom is the smallest indivisible part. Chemistry advancements showed that yes, we could distribute or we could split up that atom into protons, neutrons, and electrons. Because of this split in protons, neutrons, and electrons, it means that we could now adequately represent the charges carried by that atom. We could represent what happens when the atom had positive charges. We could represent when the atom had negative charges. We could represent how that atom could carry out bondings, could go into reactions, or could go into sharing or gifting or accepting electrons, as the case might be. All of these concepts were packed in from the discovery of this constituent of an atom. Of course, we also looked at what happened when we picked groups of atoms together that carried charges and still acted as a single unit. Because of discussions like this, we talked about terms like the radical, which were obviously terms that had very big importance in the charge and the valency they carried and their combining powers. And then, of course, we defined that the valency was the combining power of that element. And then we defined that with the concept of radicals, we could find groups of atoms that would combine together, carry like charges, and then act as a single unit. Of course, we still talked about the fact that for a single element, we could still represent the charge on that element. Remember that we defined that the oxidation number of an element is the charge that element appears to have, right? Is the charge that element appears to have. And then if the element happens to have a positive charge, we would say that element would then react to become a cation. And then if it had a negative charge, it will react to be an anion. In fact, we could say that the ions themselves are just charged elements, right? So we looked at concepts of the cation and then the anion. Great. Now, moving from that concept, we now looked at what happened when we try to stabilize these elements by combining them together. Of course, we talked about the fact that there are some elements that do not even need to go into reactions at all. We call those elements as members of a group with them as inert gases, or as noble gases, or as group 0 elements, or sometimes as group 8 elements. We talk about the fact that those elements had complete structures in their outer shell. Complete structures in the sense that they had either a duplet structure in the case of helium, or the octet structure in the case of elements like neon. This was very, very important because we now saw that all the other elements that could not form inert or could not become members of inert gases now had to react or excite themselves into becoming like those inert gases. In essence, they were trying to achieve nobility or stability by becoming inert gases. In essence, it meant that they were always going to be trying to either achieve the octet structure, which is the usual case, or the duplet structure, which is the rare case. We talked about the fact that if we say the duplet structure, we are talking about the 2 structure, which means that it has 2 electrons in the outer shell. And if we say the octet structure, we are simply talking about the 8 structure, where we have a complete 8 valence electrons in the outer shell. We talked about all these concepts. Now, of course, because those elements are trying to become stable, it means that they will react with elements that share the opposite predicament. For instance, an element that is trying to get rid of one valence electron to become stable will be content to combine with another element that needs one valence electron to also become stable. A good example is the reaction that happens between sodium and chlorine. Sodium with one electron available to give out, chlorine with one electron needed to collect. Sodium will combine with chlorine and giving us sodium chloride, thus attaining nobility or stability. Elements combining in that form now gives us a new concept, which is the concept of compounds. We talk about the fact that compounds themselves are stable forms that arise after the combination of two elements that have been charged up so that they can attain stability together. We also talked about ways in which we could name those compounds via using the system of naming developed by the International Union of Pure and Applied Chemistry, which is the IUPAC. We talked about what happens when we try to generate the subscripts of those radicals. Of course, the subscripts are very, very important because whenever you are now balancing those equations, you cannot change the subscripts. So they have to be in a standard form. We also talked about how to name compounds that are already stable via calculation of the oxidation number of the elements in the middle of that compound. All of this we looked at in detail in our last session. We now wrapped up the last session by looking at the difference between what we call a compound, which is chemically combined, and what we call a mixture, which is just bringing two or more constituents together without any chemical reaction between them. We looked at concepts like needs of energy, needs of chemical bonding, reaction time, their stability, their form, their different states. For instance, compounds, once they come together, will have just one single state, but then mixtures, when they come together, can still retain their original states. You can have liquid and solid mixing together, and you still have those solid and liquid still showing. Today, we are now going to look deeply into that concept of mixtures. Today, we are going to consider, or we are going to concern ourselves with how we can correctly separate those mixtures from each other. This is because in real life, mixtures are much more common to humans or are much more accessible to humans than the compounds which are usually prepared in the labs. For instance, it is going to be very, very hard for normal humans to come across ammonium chloride in the natural form unless you are in a laboratory. However, almost every human has come across Gary and water mixed together, giving us Gary solution, or as we usually called it in elementary days, the Garium solution. We have other mixtures as well. You could mix salt and water. You could mix camphor with common salt. You could mix mothball with sand. Mothball being what we usually put, that white ball we usually put in clothes to prevent all those moths coming on the clothes and spoiling them. We could have so many mixtures coming together. How then can we separate those mixtures together? For instance, if you have Gary and water, you would naturally feel like the moment the Gary has been soaked up by that water, it becomes very, very hard for you to get the dry Gary itself. However, there are techniques that can help you get that Gary itself. If you were to have iron filings mistakenly poured into sand, you'd wonder that, oh, I've missed those iron filings because of their small nature. However, there are techniques that can help us sieve out or take out those iron filings from the sand. We are going to be looking at the key techniques one after the other today. Now, we are going to begin our journey into separation techniques. So I'm just going to write that here. Separation techniques. So, today we are going to begin our journey into separation techniques from simple to complex. We are going to look at the simplest separation techniques that we are usually familiar with, or that we are very, very common with, and that is the sieving. Sieving. Now, the major instrument used in the sieving technique is the sieve, or sometimes what we call the mesh sieve. Now, what is the purpose of the sieving technique? The sieving technique is a technique that helps us sieve or separate particles of different sizes. Now, that's the most important thing. The sieving technique separates mixtures of different sizes. So let's just quote that here. Mixtures of different sizes. So when we are talking about separation techniques, the most important thing, and this is where questions come out from, is that we must be able to identify the distinct features of the mixtures that are separated within the different techniques. For instance, for sieving, the mixtures have to have different sizes. Now, it means that definitely, it obviously means that if you are now talking about different sizes, then it follows that the mixtures has to be uniformly in a solid state, because it's only solids that will have comparisons in terms of sizes. So it means that the sieving technique, one first and foremost, is a technique used for solids. Two, it's a technique that centers heavily on the use of mixtures that have different sizes. These are the two key takeaways for the sieving technique: different size and its solids. So this would help you narrow down when you have two constituents given to you, and then you are asked, how do we separate these constituents? And you look at them. Okay, these two constituents I'm giving, what is their state? They are both solids. It narrows down the options you have. Okay, these two solids, can I look at their sizes? Can I differentiate their sizes? This gives you a much more deeper understanding of the techniques they can use. Let's continue to talk about the sieving technique. Now, we have said that the most important instrument for the sieving technique is the mesh sieve. The mesh sieve. Now, using this mesh sieve, how does it work? Remember, we have said that it separates mixtures of different sizes. So it means that the basic principle for sieving is that you pour all your mixture on top of the sieve. You sieve or you shake the sieve, and then the smaller sized particles or constituents of that mixture comes below the sieve. That is the simplest way in which the sieving technique is used. A good example of this is during garri production. We are going to be using garri a lot. Why? Because in this environment, garri is one of the most easily accessible resource we can have. In garri production, if you are very close to all those old women, when they are producing garri, you'll find out that after they have finished the process of getting it out of the fire, they are pouring it on a sieve after it has cooled down. And then they are shaking the sieve. You will find out that once they shake the sieve, particles start falling from that sieve. Now, those particles are actually the pure form of the garri itself. Those ones coming down the sieve are of ideal sizes and are of finely constructed constituents, which means that they have no hard parts, they have no extra big parts. It's of refined sizes. And then once they are done with the process and you look on top of the sieve, you would find out that what you would have on top of the sieve are those ones with inappropriate sizes. We usually call those ones the shafts. This is very, very important in the production of the garri itself. Another way you can look at it is if you have your rice in your house and then mistakenly maybe you have a kid brother or a kid sister, and then she's supposed to get the rice for you, and then the rice pours into sand. You don't need to worry so much. First off, you can just get back the mixture that you now have of sand and rice and get a sieve. Obviously, you would find out that normally the sand particles are obviously of the smallest constituent form you can get. So if you have to pour it on a sieve, the sands will usually be the one to come below the sieve platform. And then you have rice on top. So you'd find out that what you'd have on top, which is rice now, is what is taking the position of the shaft in the garri production, where the garri which came down was the clean one we wanted. But in this case, the sand that is coming down is no longer the clean one we want. What we want is now what is on top of the sieve, which is the rice. Of course, you might still have to carry out much more separation techniques on that rice on top, because for instance, if the sand was mixed with stone, then there's a possibility that the stone won't come down on the sieve, because the stone is obviously of a bigger size than the rice, so they will stay on top. And then you can still carry out a sieving technique again using a mesh sieve of a greater hole. So you find out that these sieves have different measurements. Usually they form a pattern like this that looks like a draft pattern, and then these holes in between have standard sizes. Some of those sizes are small, some of those sizes are big. You can find sieves of different sizes, and so you can just move on to use a bigger sieve that has a bigger size that will only allow the size limit of the rice to come down. This is practical use of the sieve. Second example we are going to be talking about, or the second separation technique we are going to be talking about, is the filtration technique. Now, for the filtration technique, of course, we have looked at the technique where we are mixing predominantly solids. Let's look at what happens when we have two different states mixed together. For the filtration technique, we are simply talking about a technique that helps us separate between solids and liquids. Helps us separate between solids and liquids. Of course, you'd obviously realize that if you were to pour a solid and liquid mixture into the sieve, it would make so much, not a lot of difference, right? Because the liquid will obviously go down the sieve, because regardless of whatever net hole you use, the liquid will always flow down. So, and then the solid you'd have on top might not be completely devoid of the liquid. So there is no guarantee that you'd have what exactly you want. However, with the filtration method, which uses the filter paper, you would find out that the goal of the filter paper is to allow only the liquid through the filtration process. So when you have a mixture of solid and liquid and you pour it through the filter paper, you would find out that there is absolutely no way that the solid will get through the filter paper and mix with the liquid any longer. The liquid will be the only one to pass through the filter paper. A good example of a mixture you can separate using the filter paper is again our garri solution. You'll find out that when you want to drink your garri, you pour your garri into a cup and then you pour water into the garri. You find out that, oh, okay, probably you feel like, it's not yet time for me to drink this garri. Maybe I was 2 minutes early. Maybe I need to get myself granuts or kuli or day after. And then I need to get more items to make this garri worth drinking. And be like, if I were to leave the garri into the water, the garri will continue to get softer and softer and I might not enjoy the taste anymore. So let's take off the water. And then you can pour the garri solution through the filter paper. You'll find out that the water comes down and you will still have your garri intact on the filter paper. This will help you separate the water away from the garri as soon as possible without any stress. Now, when you carry out the filtration process, one major thing, it's very important to take note of one major thing. For the filtration process, what remains on top of the filter paper has a name. What flows through the filter paper downwards also has a name. Now, for the filter paper, if you were to have the filter paper and then you were to pour from your filter paper the solution, as you have water on top, and then you have the solid. If you were to pour this through the filter paper into, let's say, your beaker, the solution that comes in here or that flows through the filter paper is called the filtrate. And then that solid that remains on the filter paper is termed the residue. That's it. Once you carry out the filter paper process, what stays on the filter paper is the residue. What flows through the filter paper is the filtrate. So you might wonder, okay, now, this looks nice, all well and good. But use the filter paper as it is, there's a guarantee that, or there's a possibility that I might not be able to hold all the solids I have. You can also use your filter paper with or using the head of a funnel. So using the funnel will mean that you now have larger room, and then you can simply place your filter paper in the bottom hole of the funnel. For instance, you have, let's say you have this as your funnel structure. This is the hole that comes down through the funnel. You have your beaker here. And then here, you are pouring in your solution as expected. But then, you don't want it to flow just through down because that means the process is useless. So you can place your filter paper here such that once that liquid comes in with that solid, once everything comes in, only the purified, I won't say purified now, but only the liquid, which in this case is that pure form we want, goes into the beaker. So what happens here is still your filtrate, and what stays here inside the funnel is your residue. So either you use the filter paper alone or use the filter paper with the assistance of a funnel, that's fine. Any of the method works brilliantly. Now that we have looked at that, let's take another kind of separation technique and see how we can utilize that. Now, for our third filtration or for our third separation technique, we are going to be using something very, very common, and that is the technique of magnetization. Now, by the magnetization process, in fact, by the name itself, you know exactly what we are talking about. The major instrument we need for the magnetization process to work is the existence of the magnetic property. So, it makes sense. Where sieving, we needed mixtures of different sizes. Where filtration, we needed a solid and a liquid. For magnetism or for magnetization, all we just need to care about is magnetic property. In essence, it means that we can only use magnetization as a technique if one of the constituents of that mixture has a magnetic property. So we are talking about mixtures where one of the constituents is magnetic, or in better terms, has the magnetic property. And this is very, very interesting, right? So it means that even if you have 2 or 3 or 4 constituents inside, and then you want to separate them,